So welcome everybody to this third series of the DP Roy Memorial Lectures. Of course, those who are in TIFR know DP very well. For those who are here, let's say on Zoom and also following us on YouTube, Professor DP Roy was a very dear colleague, very dear senior colleague who was in TIFR for many years, and I did overlap with him in the early part of my days in TIFR, working in particle physics phenomenology. And this is a public lecture in his honor. Before we start, let me invite the director of TIFR, Professor Ramakrishnan, to say a few words to start.
Thank you, Amol. And first of all, I am glad to be part of this memorial meeting. Let me welcome all of you to this third memorial meeting of Professor D.P. Roy. And though I am an experimentalist, I have seen Professor D.P. Roy, the way he interacts with the experimentalist is a sight to see in the West Canteen tea times, you know, and he gets really animated and catch holds of people like Professor Ganguly and Gurtu and Nabo Mandal. None of the experimentalists can escape from him. And so any collider research comes from him, and he is, you know, those days he will be hyperactive also. And the way he, you know, the way he interacts with his juniors and, you know, help them along, mentoring them, it's a sight to watch. I mean, I'm a condensed matter experimentalist, but I always envy him because the way he nurtured the people in the experimental side, I think high energy experimental physics as well. I mean, his work, he had done seminal work on particle physics and astroparticle physics, and TIFR was fortunate to have him more than 4 decades. I mean, it's words cannot describe the contributions he has done, and also the contributions he has done for the HBCSE, Home Yoga Center for Science Education, and truly a remarkable man. And it is very appropriate that another, you know, well-known theoretical physicist, Professor Rohini Godbole, is giving the public lecture today. And like all of you, I am also eagerly waiting to hear the lecture on the where she is going to shed light on the dark matter. Thank you, Amol.
Thank you, Professor Ramakrishnan. I would now like to request Professor Gautam Mandal, the chairperson of the Department of Theoretical Physics, to say a few words about DP Roy Memorial Lectures.
Thank you, Amol. So, good afternoon, all. On behalf of the Department of Theoretical Physics at TIFR, it is a great pleasure to welcome you all to the third DP Roy Memorial Public Lecture. Professor D.P. Roy was a leading figure in the field of high energy physics phenomenology in India and made crucial contributions to build activity in this area in the country and in particular in TIFR. The D.P. Roy Memorial Lectures are made possible by the generosity of Mrs. Monica Roy and the family of the late Professor Roy. The first 2 lectures in the series were delivered by Professor Christophe Grosjean of DAISY and Professor Kate Schulberg of the Duke University on the subjects of physics beyond the standard model and neutrino physics. Today's lecture will be delivered by Professor Rohini Godbole of the IISc Bangalore, who is a leading eminent particle physicist of our country and a long-time collaborator of Professor D.P. Roy.
Thank you, Gautam. This lecture series is, of course, started at the initiative of Mrs. Monica Roy and the family of Professor D.P. Roy. And we are very happy that she could actually join us on Zoom. Monica, do you want to say a few words? Start with. You may have to unmute yourself. Yes.
Yes, unmuted. Okay. First of all, I would like to thank you, TIFR and Director TIFR Theory Group, and all of you for arranging this beautiful lecture series. And it's very nostalgic moment for me. And especially see Rohini to give the lecture. Rohini has a long association with Professor D.P. Roy and our family. I remember in 1979 when Rohini joined TIFR, DP was doing some collaboration work with her. And she said that she is very good. I am learning the computer part from Rohini. She is extremely good. DP did not know much of computers in those days, and he was learning. So it's a very appropriate, she is very appropriate person to call for this lecture. And next time I remember when we were in Dortmund, PP was working with Rhea. Rhea asked that, can you recommend somebody from your group for next visiting fellow to this institute? So DP recommended Rohini. Then he told me, I am recommended her. I hope she will do a good work. And she has proved that. And I am very, very happy that Rohini came. I am very happy for you. After 2 years of pandemic, you have managed to arrange this lecture series. And DP wanted part of his savings should go as a donation for good work. And I am the custodian, and that is what I have done. And I am very happy that TIFR has accepted my wish and taking all efforts to make it a success. That's all. We are eagerly waiting for Rohini. I also like Rohini's cause for women, especially the women scientists. That I appreciate very much. And I wish her more and more success in her life.
Thank you.
And DP, wherever he is, he will definitely be happy. Thank you.
Thank you, Monika ji. We always remember DP with fondness, both his science as well as through his interactions. So it's an honor to be hosting this lecture series in his honor. Professor Amitava Datta has been a long-time collaborator of DP, and I now invite him to say a few words about DP's scientific work. Amitava, you have to unmute yourself.
Yeah, can you hear me?
Yes, we can.
Yeah, thank you, everybody. Following the Bengali custom, I used to call DP Durgada, elder brother Durga. And indeed, he was an elder brother, not only in terms of fondness, but he simply guided us. A whole generation of physicists who could enjoy the excitement of one discovery after another at Hadron colliders in India were indeed guided by DP. Of course, Rohini was a very able collaborator that DP was lucky to find. And the tradition of doing high energy collider physics gradually took root in India. But when I first saw Durgada in the early 70s of the last century, he was doing at the other end of the spectrum, which are known as low energy strong interactions, and made many contributions there. I am not very competent to understand all those, but he indeed had a good reputation in that area. But in no time, when the high energy physics in the true sense of the word, discovering of heavy particles at high energy machines came, DP immediately jumped into it. And as I said, Rohini was there, and they indeed contributed very significantly. The first one has to recall the discovery of the top quark, which in fact is one of the heaviest undiscovered particles in those days. And DP and collaborators gave a very nice technique for discovering it. In a Hadron Collider, there are a lot of debris, and finding out the signal from the background is not an easy job. And DP and his collaborators, namely Shandip Pagwasa and Rohini, they did a very good job, which was followed by the experimentalists for a long time. DP also made significant contributions to new physics. Top quark, etc., were in a sense part of the standard model. But of course, for various reasons, people were talking about more novel physics, the so-called beyond standard model. And DP's contribution to beyond standard model was also very, very significant. First was a proposal for discovering supersymmetric particles, a new kind of symmetry. And as Monica Bodhi has already mentioned, he worked with Rhea to suggest the first significant practical way of disentangling the presence of supersymmetric particles from the debris of a Hadron Collider. And then DP went on and on, charged Higgs, which were also so-called beyond standard model physics. He made very significant contribution, which were followed by experimentalists subsequently, was discovering the charged Higgs signal from the polarization of a tau particle that may come from the Higgs. And then DP contributed significantly to dark matter physics, mainly supersymmetric dark matter. You will hear about it from Rohini. And finally, I must mention that when a completely different kind of physics, non-accelerator physics, namely neutrino physics, was at its peak, people discovered the mystery, unveiled the mystery of the solar neutrinos, and DP and his collaborators were right there. They analyzed the data, made many significant contributions. So to summarize, I will simply say that practically 4 or 5 branches of very, very interesting particle physics, both accelerator based and non-accelerator based, and DP was in it. And then, of course, he always acted as a mentor to a whole generation of physics, and not only them, also their students. DP collaborated even with the students of his collaborators, a very kind man who could enlighten people very easily. I'm very glad to have this opportunity to say a few words in memory of Durgala. Thank you.
Thank you, Eddie. I now invite Professor Siru Praichaudhary to introduce today's speaker, Professor Rohini Godbole. Siru?
Thank you, Amol. Actually, when I look at the composition of today's, at least in the Zoom, of today's audience, I don't think Rohini really needs an introduction. Most people know her very well, though I do see a few youngsters, and so I will go through the motions. But to tell the truth, Rohini, at least in TIFR, needs no introduction. Anyway, let me still, it is a privilege and an honor to be able to do this introduction. So let me tell you a little about Rohini's life and career. She did her BSc from Pune in 1972 and her MSc from IIT Bombay in 1974. Both of these, she was the topper in her batch. Then she went to Stony Brook, sunny Stony Brook, to do her PhD, which she finished in 1979. After that, she came back to TIFR and a postdoc here till 1982. And it is during this postdoc period that she began to collaborate with DP, as Eri has already told you some of these, Professor Datta. And they were, in some sense, the pioneers of collider physics in India. Then in 1982, I think Rohini briefly moved to the Institute of Science for a short time, and then she joined the University of Bombay Department of Physics, where she was there for a long time till 1995. After 1995, she has moved to the Indian Institute of Science at Bangalore, and then she joined what was the Center for Theoretical Studies and now has become the Center for High Energy Physics. And she is still there and in a senior position. Rohini has secured many awards and many honors during her lifetime. I don't want to go through the full list, but two I have to mention. In 2009, she was awarded the Padma Shri. And in 2021, which was last year, the National Order of Merit of France. I can't pronounce it in French, but that's what it means. Apart from this, Rohini has written more than 300 papers during her career. And as I said, she was a pioneer with D.P. Roy of collider and beyond standard model physics in India. And maybe I could add a little bit of a personal reminiscence here, that there was a time when, as a student, I and my mentors, including Professor Amitava Datta, Amitava Raichandri, and our other students, we all wanted to learn what was this collider physics. And it was at that time that Professor D.P. Roy and Rohini Godbole, together they came to Kolkata to the WICC and organized a workshop. And it was from that workshop that many of us in India got our first introduction to collider physics, on which many of us have worked for the rest of our careers. So it is a very happy occasion to be on this occasion with one of our mentors or teachers giving a memorial lecture for the other. Apart from this, Rohini is also the author of a very well-known book on supersymmetry, which she co-authored with Probir Roy and Manuel Dries. And this is one of the standard books one refers to for supersymmetry. Whether supersymmetry, it's worth reading this book anymore, she will tell us tomorrow. And more important, I think for the last several years, Rohini has been a pioneer of the women in science movement in India. She was the co-author with Ram Ramaswamy of a book called Lilavati's Daughters, brought out in 2008 by the Indian Academy of Sciences. I think she was, and she still is perhaps, chair of the Women in Science section of the Indian Academy of Sciences. And I think she has done pioneering work in this, not only by raising the awareness, but by her own example. I think it is, I think for aspiring women scientists, the example of Rohini Godbole and how she has worked and achieved things in her career must be a great inspiration. So with these words, which I think have been redundant for most of the audience, let me invite Rohini. So I noticed one thing, that the word light has featured in many, many talks by Rohini, from the structure of light to from photons to various things. And today she will shed light, of course, on something which doesn't shed light on its own, that is dark matter. So Rohini, please.
So thank you very much, Sri Roop. And first, let me begin by thanking the D.P. Roy Memorial Committee for asking me to talk here. And indeed, it's truly a great pleasure. I mean, one uses these words, but I don't think I would have meant these words ever any more than what I mean today. And going back to, for me, as again, Sri Roop said correctly, giving a talk in TIFR doesn't feel like one is giving a talk anyway, it's like coming back home. So I will begin by sort of saying this, that even today, after having left Bombay, God knows how many years ago, as Sri Roop, I didn't count them just now. Whenever I go out of India, I say, oh, when I get back to Bombay, and then I correct myself and say, no, when I get back to Bangalore. So I have moved out of Bombay, out of TIFR, but TIFR and Bombay has been a part of me. And I think that has been mainly because of the very enjoyable physics that I was involved in, and I have been involved with when I was in TIFR, when I was in Bombay, and even now I remain involved. And really quite a major part of that involvement was because of DP. It began with DP. So you see that this is indeed why this is indeed an extremely important occasion for me to give this lecture and pay my express my good feelings, my tribute, my homage, whatever word you want to use, to my senior collaborator, but even more importantly, you know, when I joined TIFR, he was a senior collaborator, senior by 10 years. But I think I didn't know when he became a friend with whom you argued, you laughed, and you walked and you talked. So he had been a friend all my life, all his life, a well-wisher. And indeed, that's why when I spoke with Monica, when I got the Padma Shri, one of the thoughts that came to my mind that DP would have been very, very happy. He had been, as has been said, he has been an extremely good mentor, and to a person who was 10 years younger to him at that time, he was indeed a good mentor directing directions in physics. So indeed, because of all this reason, it's quite emotional for me to be able to give this lecture in his memory. So having said these things, let me now begin sort of at the business end, and let me try to share the screen. And let me just see for a minute. Yeah, share screen. So this is the topic on which I want to talk, namely shedding light on the dark matter in the universe. But as you would see that since the subject is extremely vast, I have kind of put in the bracket to reduce the extent to which I would discuss it at the Large Hadron Collider. Of course, it's not a sort of surprise that I do this, because that's where my area of expertise ends. So indeed, this is I'm very pleased again to give this D.P. Roy Memorial Lecture. And as I have written here, for many of us, he was just DP. And even for the international community, he was always DP. And I would once again say this, that you will always be fondly remembered DP for the scientist that you were, but more importantly to me at this age in my life, more importantly also for the human being that you were. So this is now my attempt to sort of describe the current status of the subject, one of the subjects in which DP was interested. So I will begin by kind of giving a very generic description of the current frontiers of exploration in high energy physics. And then I will spend actually quite some time in talking about what is dark matter and what are the questions it asks us. And then a very pragmatic question: how does one hunt for something that is dark? And how does one shed light on something that is dark? And I would say that in the course of events, I hope I get to describe a piece of work that was made by myself and DP, which has not yet been mentioned, and which actually does have some connection to this theme. And then, of course, I would like to talk about what can one do at the Large Hadron Collider. So what is this accepted worldview? The accepted worldview, after God knows, about 150 years, since since the discovery of the electron, now 125, 35 years, let's say. Now the subject of elementary particle physics has sort of come of age, and the accepted worldview is that the fundamental particles in the world are quarks, the leptons, those are the matter particles, and there exist 4 fundamental forces, and these forces are also exchanged by fundamental particles, that is the force carriers, which are called bosons, the photon, the W and the Z boson, the gluons, and of course, the omnipresent Higgs boson. And what we know, and that is, I think, the first part of, I'm trying to say why this subject is of interest to a particle physicist, it comes here, that the laws of particle physics, which we have found to be functioning at distant scales of Fermis and smaller, they seem to be of relevance in addressing things that happen on cosmological timescales, that is, at the beginning of the universe, and at astronomical distance scales, that is millions of parsecs and above. And just to give an idea, 1 parsec is 3.27 light years. And questions such as, how was everything formed? How did the nucleons form? Can we explain the relative abundance of different elements in the universe? How did the stars form? How did the galaxies form? And understanding of these questions completely actually also needs the knowledge of standard model of particle physics, along with astrophysics, cosmology, plasma physics, and what have you. So that is the kind of reason why what I showed you on this slide is not just of relevance to maybe the 10,000 particle physicists in the world, but it is of relevance to a much broader concept and the subject that we are trying to investigate. And also particle physics today finds itself, and for the past 10 years almost now, and it's becoming curiouser and curiouser, as you would say, as time goes along. And to ape Sri Roop, I would steal from a first line of one of his talks, which he gave 10 years ago, because I really loved it. And this is basically stealing from the first line of The Tale of Two Cities, which is, it is the best of the times and it is the worst of the times. Indeed, for particle physics, we have found the standard model heads. We have proved the standard model to an incredible accuracy. And we have no glimmer of particles or interactions that we believe must exist outside the framework of the standard model, what we call BSM, that is promised to us by the properties of the observed Higgs boson. So this is the story. The standard model of particle physics now is actually, these are laws of motion of all these fundamental particles whose list I made here. The laws of motion of these fundamental particles under the action of these fundamental forces is really, they can be derived from this Lagrangian. For all us physicists, we know that once we have a Lagrangian, we can write down equations of motions. So this is the Lagrangian of all the fundamental particles in the universe and all the fundamental force carriers and how they move with each other. So then, in some sense, you can say, oh, the journey is over. But of course, the journey is not over. The answer is no. Now, is it only because we particle physicists, of course, won't like to lose our jobs? So actually not. I already made a connection and I will now make it more clear that there are many cosmological observations which lack an understanding or have an incomplete understanding, and they are reasonably, important observations. These are puzzles that we have not, that is the scientists have not yet been able to sort out. And these puzzles are really relevant for particle physics because of the complex cosmic implications of the theories of particle physics. Actually, the giants like Bethe, Gamow, Weinberg, they were the ones who began, taking first steps on this path to explore these cosmic connections. And that is now, in some sense, the leading edge of particle physics. And these puzzles are actually the pragmatic reasons which make us believe in physics, either particles or interactions beyond the ones that exist in the standard model, which I put forward in my first slide. And that's called BSM, Beyond Standard Model. So let me mention here, I will go, as I go along, time and again, I will mention, when I mention something that is DP was involved in. So let me mention here that the BSM actually formed a very big part of the canvas on which DP painted most of his intellectual scientific life. So what are these cosmic reasons? One is that there is dark matter in the universe. There seems to exist a lot of matter in the universe that does not shine. And, this was a reasonably controversial subject for a long time. I will give you a little bit of an history. But finally, now it has been, it's a done deal. Nobel Prize has been given in 2019 for work, which actually demonstrates conclusively that dark matter exists in the universe. As already told to you, DP actually worked on it in the context of supersymmetric dark matter. The second puzzle is matter-antimatter asymmetry in the universe. That even though at the beginning of the universe, there was an equal amount of matter and antimatter, in today's universe, we have complete dominance of matter. And the short form for this is baryonic asymmetry in the universe, BAU. We don't have a good theoretical understanding for this in the context of particle physics, but we have a qualitative understanding. And that's what sort of drives the need of BSM, because it tells us that without BSM, we don't seem to be able to account for the entire asymmetry, baryonic asymmetry in the universe. And the last but not the least is the universe seemed to be accelerating dark energy. This was indeed, honored by a Nobel Prize with this experimental discovery in 2011. So these are the three cosmic connections which make us believe that particle physics has future beyond the standard model. From the perspective of a particle physicist, there are actually additional, more aesthetic, more theoretical reasons for expecting BSM. Let me list them, but I'm not going to discuss them. One is that electroweak scale, what we call it, which is the scale at which the electroweak symmetry, the scale of electroweak theory. This is unstable under radiative corrections, and unless we think of some bigger symmetry. This was again partially talked about by Amitabh Datta. The other simpler words is that we want to know why the mass of the Higgs is as small or comparable to the mass of the WZ and the top quark is, because in principle, theoretically, the Higgs mass could have had any value much, much far away from this scale. But as it happens, the value is very close to this mass scale of electroweak mass scale. And the Higgs discovery was, of course, in 2013, when we knew that the mass is indeed the electroweak scale. And one of the solutions which allow to us to understand what keeps the balloon of the Higgs mass, steadily fixed to the ground, that is actually supersymmetry. And DP actually worked really a lot on Higgs physics, already described by Amitabh also, supersymmetry, which was a cure to this problem. Then the third puzzle that is there for the theorist, second puzzle, is the non-zero mass of the neutrinos, which got the Nobel Prize in 2015. And a need to get a basic understanding, not just of the non-zero mass of the neutrinos, but a basic understanding of the non-fermion masses, their hierarchy, and the entire structure. And again, DP really contributed to the neutrino oscillation phenomenology in a very major way, which is a phenomenological study of the topic. Then unification of couplings, as well as inclusion of gravity in the picture. So these are, from the theorist's perspective, reasons for imagining physics beyond standard model. These are the three, which are sort of what I call pragmatic reasons to expect physics beyond standard model, the experimental signals to expect physics beyond standard model. So let's begin with the dark matter. That the contents of our periodic table seem to account only for 5% of the total matter in the universe. And I will mention some of the astrophysical evidence, and this astrophysical evidence is pretty convincing now. It was not always so. And this dark matter, if it has to be one of the particles in the standard model periodic table, the only guy which could have fitted the bill, guy or the gal, will be neutrino. But unfortunately, neutrino cannot be the dark matter. I will come to the reasons why it cannot be the dark matter. And as a result of that, we know that the experimental observation of dark matter tells us that there should be at least one particle beyond the standard model, which does not decay and which lives at least on the time scale of the life of the universe. And this is the energy budget of the universe, where 5% is baryonic matter, about 27% is dark matter, and the remaining is dark energy, which, as I said, I will not touch, but about dark matter and baryonic matter, about dark matter, I would discuss. Now here I want to emphasize that we can draw this conclusion that 27% is dark matter only because, and that this dark matter cannot be neutrino. Both these conclusions we can draw because we understand the interactions of all the SM particles perfectly. And that is where we are able to draw this conclusion that the existence of dark matter indeed needs some physics beyond standard model. So let's begin at the beginning. As Julie Andrews said in Sound of Music, let's start at the beginning, a good place to begin. So where did the astrophysical evidence for dark matter start? It started from Lord Kelvin, actually. For most people, it actually started from Zwicky, who actually tried to extract the mass of the galaxy from the galaxy dynamics. And he concluded that there must be much more than what we see, the mass, because the galaxy is being held together by, if the galaxy has to be held together by gravitation at the major velocity. So this was simply virial theorem that the kinetic energy and potential energy average should be equal. And this was as simple as that. This was actually put firmly in place by Vera-Rubin's measurements of rotational curves. And that is, I will try to give a very simple understanding of what the kind of work that was done and the basic idea behind it. So she measured the rotational curves. Now in spiral galaxies, which are the most common among galaxies, the stars rotate, okay? They rotate about a center. Now, if we know what Newton taught us, we expect the stars closer to the center to rotate faster. Why? Because there is this simple formula that the velocity of the stars around the center should be given by G, the Newton's coupling constant, times the total mass that is enclosed around which these stars are rotating at the center. As because of Gauss's theorem, we can take it all to be concentrated at the center divided by R. So if there is a far star at a distance F, and if there is a near star at a distance Rn, then if Rf is equal to twice Rn, then you expect the stars at F to move twice as slow. And observations by Vera-Rubin and many others later showed us that reality was very, very different. And this meant, what their observations meant, that the enclosed mass M had also to increase as the radius R of the orbit increased. And this is Vera-Rubin with her observations. And this is what was expected. This A pattern is what was expected if we use this simple formula and if we used all the mass that we saw with our telescopes, that is the visible mass. So clearly, if visible mass, if you put value of M here, then you found that as the distance increased, this guy had to go like this. But in reality, it went like this. And that indeed people could use to estimate, so to say, a mass that gets enclosed that we cannot see, and that is the dark matter. So this is just to show you one of the first measurements by Rubin and Ford. These blue points are blue or black. I don't know what color you can see here, but these are Vera-Rubin and Ford's points. And Babcock had made some measurements just before that, quite a bit earlier, but those measurements were this year, so they really had not gone very far. And now these measurements have been now since then from 1970. Today, this is the galaxy M33, and the rotational velocity of the stars has been measured by various different methods. These are extremely complex and very difficult, I would say, astronomical measurements from very different sources. And now this is confirmed that the rotational curves of the stars in this particular galaxy here and many other galaxies actually go up like this as the distance from the center goes on increasing. The distance is in light years. This is 10,000 light years, 20,000 light years, 30,000 light years. So place where you start seeing the effects begins around 10,000 light years. And this is the velocity of rotation. And notice that, we are talking of distances which are kiloparsecs. Okay. Now, following this, there are two other evidences that came for dark matter. And that is what I meant by saying that the early history was questionable. People used to question even whether this really requires dark matter, but such beautiful measurements were followed up by another wonderful measurement, and this is the bullet cluster, and this is at the galaxy cluster level. I will explain in the next slide what this is, but this is a picture of a collision of galaxies in bullet cluster, and the blue actually is the picture which has been taken by gravitational lensing, and the red is the picture that has been taken by X-rays, and this actually tells us that galaxies contain matter which does not shine, so it is not seen in the X-rays, but it is definitely seen in the gravitational lensing. And last, this is at the megaparsec level, and that is the galaxy clusters, and then at the scale of the universe, that is gigaparsec, and that is really at the beginning of the universe, there is this cosmic microwave background anisotropy measurement. So there is a background radiation in the cosmic background radiation, as the name says, and you make these measurements, and then you find that the temperature is not exactly the same in all directions, and there are small anisotropies. And these small anisotropies indeed are indicative of the structure formations, because they are anisotropies in the structure of the universe at that time, and therefore they are related to the structures that we see today. So these are the two ones, one at the megaparsec level and one at the gigaparsec levels. So at all different distance scales. So as I said, in the bullet cluster, galaxy collision was pictured, and the blue was the picture obtained using gravitational lensing. Red was the image obtained in X-rays. Again, I remind you of this. And there is a more matter in these clusters than we can see through the X-rays. So there was dark matter. Now, actually, this is a very active area of astronomical and astrophysical research. More and more distant galaxy clusters are being seen. People are trying to obtain information about the dark matter in the universe from the effect of the intervening bodies on the image of galaxies. And the dark matter, this is like a dark matter imaging, like we see crystal structures, maybe through diffraction patterns. So this very exciting area of research. And as I said, the measurements of the cosmic microwave background radiation anisotropy actually tells us existence of the dark matter at the distant scale of the visible universe. And if you want to think in terms of time, since the universe has been expanding since the beginning, this is the physics that took place, it's a reflection of the physics that took place almost very close to the beginning of the universe. And this is actually a long story of the interplay between astrophysics and cosmology, which I wouldn't even go through. But a net result for a non-astrophysicist, astronomer, and cosmologist is that we have now strong evidence of dark matter's existence at all scales. Galaxies was the distant scale that where our Rubin began at, clusters of galaxies at megaparsec, and the observable universe at gigaparsec. So we have dark matter even on the Earth and the Sun, but its density is much, much higher in places like galaxy centers, and that is where we begin to we even try to look for. So what do we know about it? This is dark. Apart from the fact that it is dark, what else do we know about dark matter? We know that it forms 26.8% of the energy budget of the universe, and this really comes from this. You may not believe it, but it comes from these measurements, this cosmic microwave background anisotropy in the radiation that you see. You match it with the anisotropy or the structure formation that you get. So you have to actually run very often the galactic simulation models and understand the structure formation, and then from that you extract the amount of the energy the dark matter that would exist, and that's how you get this 26.8%. The dark matter velocities now are about 200 kilometers per second. So compared to velocity of light, they're really, really small. And once again, let me repeat that the direct experimental evidence, which is here, all the direct experimental evidence that exists, all the three pieces are only for their gravitational interaction. It is electromagnetically neutral and has got to be stable on the scale of the lifetime of the universe, that is few billion years. And it has to be stable on the scale of the lifetime of the universe for the simple reason that it is produced at the beginning of the universe and it is still around, and it has got implications for structure formation in the early universe. And that's where we use this microwave background radiation to get information about dark matter. All right. So this is what, that is all that we know about dark matter, frankly. Do we know anything more? Actually not, but as I said, knowing cosmology and what the cosmologists and astrophysicists know actually helps us a lot to understand more and more the possibilities of what the dark matter can or cannot do. So this is a picture which I have taken from LBL, the LBNL, old sort of nice picture, which you might have seen many, many times. And this is the history of the universe. And this is the Big Bang. This is the time inflationary period. We will not, talk much about this at all. But it is in this period that within the very short time after the Big Bang, within, when the energy scale was about, 1 TeV, actually one started having, as you can see here, possible dark matter effects. Then in about, 10 to the minus 6 seconds, you begin to see formation of nucleons. And then by the time you come to 3 minutes, the famous Weinberg's 3 minutes, you have actually formed nuclei and begin to form atoms in about, some years after that. And then you start forming structures, you start forming galaxies, and here we are. And right now, sitting here, by studying cosmic microwave background radiation, we are getting information from this period. And that is where we are getting some information about the dark matter, which would have existed and which would have been produced in this period before. And that is where things are. So, I liked here a statement from Gamow, which is very nice, that it took less than an hour to make the atoms, a few 100 million years to make the stars and the planets, and 5 billion years to make man. Right now in my talk, I'm really interested in that history of only the first hour. So in this first hour, in the early life of the universe, very early life of the universe, it's all radiation. It's in this expanding and cooling universe, baryons are formed, that is the nucleons are formed. It's here, okay, a very short time after the formation of after the Big Bang. And these baryons are formed, and then they slowly form nuclei and then stars and galaxies. Now, what happens is that initially, this is radiation. Radiation is producing particles and antiparticles. The antiparticles and particles are colliding. And if the rate of annihilation and creation is in equilibrium, then the abundance of a particular type of particle species actually remains constant. Now, the universe is also expanding. And because the universe is also expanding, beyond a certain time, the newly created particles by our radiation cannot find the partners to annihilate. Then that particular particle species goes out of thermal equilibrium. That is the word that is used, because no longer the production and annihilation are in tune with each other. They are not in sync with each other. They are not in equilibrium. Therefore, we say that that particle species goes out of thermal equilibrium, and then the abundance of that species no longer changes after that. So the temperature at which this will happen, that is determined by the laws of particle physics. That is why the laws of particle physics play a very important role in our trying to predict what should be the density of a particular type of particles in the universe today. What is the ratio of lithium to hydrogen, or what is the ratio of baryons to photons? Particle physics laws or nuclear physics laws have some bearing on these things. So dark matter are basically relics that are left over from this early universe. And as I said, that since it had to be created in the early universe through interaction of radiation, at that time, it must have had some interactions other than the gravitation. We just don't know right now what kind of interactions the dark matter particle has. And actually, what's the second point that is very important is that the dark matter particles provide the gravitational potential well in which matter can get together and structures like stars and galaxies and so on and so forth are formed. And that is precisely why the early anisotropies in the cosmic microwave background radiation eventually get mapped, into information about the dark matter. So now let's just sort of take a few seconds break and realize that we are saying that dark matter is a relic which is left from the early universe, and the expected number of these relic particles are actually determined by the theoretical understanding of early universe, of course, and the particle content of the particles in the early universe and their interactions with each other. So this object is truly something that requires knowledge of cosmology, knowledge of astrophysics, and knowledge of particle physics. So this dark matter beast is a truly astroparticle beast. And there's a lot we don't understand. There are areas of astroparticle physics which flourish in TIFR very well today. And there are quite a few big experts, people like both in astrophysics as well as in the DTP. And you can learn from somebody like Vasu much more about dark matter than I can tell you. So strictly speaking, we do not have any observational information which will constrain its mass. But however, with the general knowledge of cosmology and astrophysics that we have of the early universe, what is normally liked is a particle which would fall out of thermal equilibrium with radiation when it is not moving at relativistic speeds. And unfortunately, since the neutrino has very small mass, neutrinos will not be satisfied at the time for the neutrinos. And therefore, we know that neutrinos cannot be the dark matter. Now, this heavier dark matter, obviously, if it has to be non-relativistic when it falls out of thermal equilibrium, that means it has to be very heavy at that temperature so that it moves with non-relativistic velocities. And that is therefore the heavier dark matter candidate. And this is called cold dark matter or CDM. And this weakly interacting massive particle paradigm actually ruled, for a very, very long time. And now it's being called in question, but it's still holding its ground quite with difficulty, but it's holding its ground. I think particle physicists absolutely loved the dark matter candidate or dark matter idea and the fact that it could be a weakly interacting massive particle from the day the idea came into life. Let me spend a few minutes on this and try to expand on it, because after all, I am a particle physicist, and this is where my own interaction with dark matter begins. So the measurements of the cosmic microwave background radiation by the experiment called Planck and the anisotropies that it measured actually tells us that a certain quantity, which is dark matter density in units, some units, which I will not go into, times the Hubble constant square, reduced Hubble constant square, is 0.120 plus minus 0.001. Now, this is the one thing that has changed in the last 3 decades. Earlier, we didn't even know we had an upper limit. We had big bands, which now we think are big bands, that it lied between 0.11 and 0.13, and now we have reduced the error. The astronomers and cosmologists have reduced the error by a factor of 1,000, and they have done wonders. So this is what has brought this whole area now into realm of actual model building and understanding whether a particular model is capable of reproducing this observed relic density. So if I denote the dark matter candidate, whatever it may be, by chi, then it is easy to show by discussion of early universe cosmology that this quantity omega dm times h cross square, which is what is measured by Planck experiment, which is nothing but the dark matter density, as I said, in certain units. N chi is the dark matter density, the particle density, m chi is its mass. So if you take the density, multiply its mass, you get the total mass density in dark matter. And as I said, you have to normalize it with certain units. And what you find is that prediction in a given model of dark matter, where you can show, excuse me, it is roughly 3 into 10 to the minus 27 centimeters square per second divided by average of annihilation cross section of the dark matter over times velocity and averaged over velocity itself. So now what is the model going to affect? The model, the particle physics model is going to give me what is sigma annihilation. It is the cosmology which is going to tell me what V is. And then you have this number sigma annihilation times V. This is the measured quantity. Now you can say, aha, in my given model, I calculate sigma annihilation. I get the V from observations, my cosmology and astrophysics, and I calculate what is expected omega chi tilde h cross square in my model, compare it with 0.120 plus minus 0.001. If it doesn't fit it, please throw away the model. It doesn't quite work that way, but indeed, at least this is the particle physicist connection with the measured dark matter relic density. So actually, the interesting part is that there is a very ready-made dark matter candidate in supersymmetry. And this was a solution, as I already was mentioned a few times. It was a solution, theoretical solution, to keep the Higgs light, to keep the Higgs balloon firmly fixed on the ground, which is experimentally proved. And the proposal was that associated with every particle, there will be a supersymmetric partner. Now, for the symmetry to solve the aesthetic problems of the standard model, we needed these partners, to have mass less than 1000 GeV. We have looked for them at the Large Hadron Collider, and we have not found any evidence so far at the Large Hadron Collider. But this is not the only line of attack. The other line of attack is that this theory has a ready-made dark matter candidate, which is a cold dark matter particle. And indeed, therefore, looking for this cold dark matter particle at the Large Hadron Collider can also be a window for supersymmetry at the Large Hadron Collider, which is different than the other supersymmetric partners. So in a given model, you may have supersymmetric partners of the protons, supersymmetric partners of the quarks, supersymmetric partners of the gluons, quarks. They may be very, very heavy. But if you have this dark matter candidate, which is basically made up of supersymmetric partners of the neutral Higgs, supersymmetric partner of the Z0, and supersymmetric partner of the two more actually Higgses that appear in in supersymmetric standard model, you might be able to probe supersymmetry in a very different manner than the standard way in which we had been looking for it and in which we have not succeeded. Incidentally, looking for supersymmetric particles in this way was something that DP had contributed very in the original days with Ewald Rea, as was mentioned by Amitabh Datta. So let me now go back to the simplest extension of the standard model, which is supersymmetric standard model. And as I said, there exists naturally a particle which is neutral on the which is neutral. We can, without doing anything extra, we can arrange for it to be stable on the that it will live on the scale of the lifetime of the universe. And lo and behold, wonder of wonders, it actually has a sigma annihilation times V averaged over velocity of the order of the magnitude 10 to the minus 26 centimeters square. So these particle physicists, we particle physicists, named this dark matter particle in our lore as chi twiddle, and that's why I used the chi earlier. Now, theory actually doesn't tell us, supersymmetric theories don't tell us what are the masses of these chi twiddles. There is a variety of them, and the lightest of them would be the dark matter candidate. But what we know is that anywhere between 10 giga electron volts to 1000 giga electron volts is the naturally expected range for these dark matter particles. So this is an ideal candidate for WIMP. So you can imagine why the imaginations of all particle physicists who are interested in supersymmetry really were caught by this one particular observation that the relic density is given by this formula. And if this is 10 to the minus 26 centimeters, then you can see that of the order of, then you can see you have hopes of getting the right relic. It's because this is only order of magnitude estimate. So one thing I must say that however well motivated, however I love it, it's just one model. And from astrophysical or cosmological arguments and all the other measurements, we really don't have any confirmed indication on the mass of the dark matter particle. So there is a range of masses allowed. And particle physicists, with their ingenuity, astroparticle physicists, I must say, for each mass range, we have a different model. The important thing is that any model that you give must give rise to a Rayleigh abundance, which is in agreement with the measurements. So what are there? What is there? Forget about all the details, but you have to, what are the two parameters? One parameter is the dark matter mass, and the second parameter is annihilation cross-section. And annihilation cross-section, as I told you, depends on the particle physics, as well as the other particles that are present in the model, and the particle physics properties of the dark matter particle, and all the other particles that are present in the model. The mass is a parameter, and velocity is the cosmological parameter. So if I really wanted to be completely agnostic, in principle, a dark matter particle with mass in this entire range, this is in GeV, beginning from 10 to the minus 10 to 10 to the 6, there are candidates all over the place. And I am going to talk only about this very small range, which is called weakly interacting massive particle, WIMP, which has a mass between, let's say, 10 to 100, 1000 GeV. And this is again just to show you that for this series, the large masses, I also told you the other parameter was sigma annihilation. And then with that sigma annihilation would also then mean what are the interaction cross sections. And indeed, this is the whole range of cross sections that you can have in the models that you are trying to construct. Not all the models are well motivated, as well motivated, for example, as SUSY. Not all models give signatures at the LHC, but that is where the dark matter phenomenology is so exciting and so complex, and at the same time, really the area which everybody wants to work in. So this is really the sort of my summary of what the dark matter is. Why is it so exciting for all particle physicists and in general astroparticle physicists to understand it? And now comes the question, how do we decide which is the correct story? Because we are very, we are full of ingenuity and we have constructed a whole lot of models. How do we decide which is the correct model? In fact, there are some who argue that simply modifying theory of gravity may be enough to explain dark matter. These are modified versions of modified theory of gravity, but I will not go into that. So now we can ask a more simple question. How will you detect it? Because it's dark and we are used to detecting particles by which leave their signatures in the detectors through their electromagnetic interactions. Now this guy is dark. This guy does not have electromagnetic interaction. So how in the world are you going to see it, quote unquote? So there are three different ways. One is direct detection. What does that mean? You take a dark matter particle, and if it hits a standard model particle, and you see the recoil of the standard model particle, good old collision, and you try to see by simple collision, mechanical, shaking it, you try to detect the existence of this dark matter particle by measuring the recoil motion of the standard model particle which it is hitting. So this is called, sort of very picturesquely, this is called shake it. So this is direct detection. Then there is an indirect detection. What is the indirect detection? If at the center of sun or these big stars, galaxies, you have dark matter in plenty, then the dark matter particle can annihilate. After all, that's what they did long back in the early universe, and then they will produce some standard model particles. And you detect these standard model particles. So you break the dark matter, you create standard model particles, and that's how you detect the dark matter in the universe, by the fact that for that you have to do a lot of work. But this is one set of experiments, and that is called indirect detection. And last but not the least, which is the one where I have done some work, that is collider production, that you take the standard model particles, they collide, and they produce a pair of dark matter particles. This reaction must have taken place in the early universe. So it must happen in the collider at some point, at some level. Can you be smart enough to devise signals for this process where a pair of dark matter particles is created in the collision of a pair of standard model particles? Okay, are they may it be quarks and antiquarks, may it be gluons or whatever, and more prosaically may it be the protons and antiprotons, or protons and protons, or electrons and positrons. So this is the three methods that I have just shown, described in words. This is the direct detection experiment, and this is xenon 1 ton. This is the LHC experiment, which tries to look for the collider searches. And this is the indirect detection, both in the IceCube experiment, as well as in the experiments which are based up in the space. So this is what it's all about. Just very simply, how do we detect it on Earth? I still thought that I should show this to you. That there works for dark matter particles if the mass is in the range of 10 to 1,000 times heavier than proton, that is 10 to 1,000 GeV, and exactly the mass range where WIMP is supposed to be, exactly the mass range where Susie would like it to be present. And in this mass range, the WIMP, when it comes, it hits, for example, a heavy nucleus, and a heavy nucleus that is used is xenon, and the nucleus will recoil. Okay, the dark matter particle, of course, you cannot detect, but you can measure the recoil energies. And this is a very difficult experiment because the typical recoil energies are of the order of 100 kilo electron volts. But now people are having, this experiment has been running for a while. I will show you the results in a minute. And now people are trying to change the detection techniques to something else rather than just measuring the recoil velocity for lighter dark matter particles, where the recoil velocities would actually be much smaller and hence not measurable, and hence this technique won't work. So this is a lot of area of lot of activity right now. So this direct detection experiments using this nuclear recoil, sort of a defining experimental results came in 2019. There is a bit of an improvement of this result by a Chinese experiment called Panda, but that's not included in my figure. But I think for the purpose of this talk, that's not quite relevant. And what this tells you is that we haven't seen any signal for the dark matter. So when you have not seen any signal, what you can do, and this is what experimentalists have done, they have put a limit on the detection cross-section. And now you can go in your model and see in your model for a mass of 10 GeV of WIMP, what is the detection cross-section that your model predicts. If it is a value, for example, 10 to the minus 44, your model point is actually already out. On the other hand, if your model predicts a cross-section of 10 to the minus 46 centimeters square, then you are still in game. So this is the sort of how you want to look at this plot. And what this plot is saying, this black line is telling you that the experimentalists have looked for it and they have been able to put limit that the direct detection cross-section for a given mass of the WIMP is less than the number on the y-axis. This is a completely model independent thing. Now you and me can take my favorite model and interpret this, what it means for your model. Now about, of course, this experiment has been many decades in coming. And before this experiment was ever performed, when it was happening, designed, there was, before this xenon 1 ton result, in fact, I will show you the summary of predictions of the cross sections that were predicted in various supersymmetric models. And there were two types of different supersymmetric models. There are a variety, and I will not spend time on that today. But therefore, in the different versions of supersymmetric standard models, you actually predict cross sections either lying in this green area or in this pink area, depending on what version of supersymmetry you are looking at. And of course, this is obtained after having put all the experimental constraints that were available from the Large Hadron Collider in 2017. So therefore, now this was the region that these people, Roshkovsky and his collaborators, had summarized in this review article. And this summarizes actually work of many, many scientists. And we are all predicting that this is the region that you should look for. And indeed, now there has been this done, experiment has happened. And what are the implications of this experiment for supersymmetric theories? I'll try to tell you in the last maybe 10 minutes of my talk. But now this is where the dark matter story is, that firstly, it exists. It can be detected on Earth in these kinds of experiments. People have failed to find it. And now we want to ask, what does it mean for the LHC? You see, when LHC was designed in 1985 or so, people actually had designed the LHC to find the hits, but one had also hoped for much, much more. One had hoped that it would give us a solution to the dark matter problem. It will give us the solution for the, what is the particle physics answer to the baryonic asymmetry of the universe. Now, we have actually climbed the mountain, so to say. We have arrived at the flag, the Higgs flag. We have arrived here. From this distance far away, we thought all these mountains were together. Now we have found that these two mountains of the dark matter and the baryonic symmetry in the universe are much further away and are much higher. And that's where the puzzle is. And how do we go from that? So I want to actually now concentrate in the last 15 to 20 minutes on a small part of the story about how can one probe the dark matter candidate in supersymmetry through joint explorations at the Large Hadron Collider, at the direct detection experiment, and the upcoming E plus E minus colliders. So in this context, I will actually talk not in very detail, but I will mention two models, and I just want you to know the names of the models. One is a minimal extension of the standard model, MSSM, and there are two parts of the one particular version of this MSSM, which is very general, and that's called phenomenological minimal supersymmetric standard model, that I will call as PMSSM, and the other is next to minimal supersymmetric standard model, that is called NMSSM. I won't give any details of this, so don't worry, but these are two versions of supersymmetric theories. What is the advantage of analyzing the dark matter phenomenology in a particular model? It's because the same parameters of the model decide the relic density, give you the prediction for the direct detection cross sections, and also give you the predictions for what is the LHC phenomenology. So we can actually study the model, a given point in the parameter space, from all these three different angles. So it's like a room has three different windows, and we can look at it through all the three windows. And then we can kind of say that if from one window we don't see it, we can see if the other window gives any evidence, and then understand why it is invisible from the other window. So therefore, this is a very interesting way of simultaneously looking at supersymmetry from three different aspects. Now, of course, the direct and indirect detection experiments or the signals that you predict do not depend on what your model is. Therefore, it does not depend on the fact that your dark matter was supersymmetric WIMP. At the LHC, some of the signals you can show are not dependent on the model, and some which are very much dependent on the model. And I will separate between the two. Now, the folklore about the SUSY dark matter by now has been that the best SUSY dark matter candidate, which is consistent with all the current SUSY searches, as well as the dark matter direct detection experiment, is actually a heavy dark matter particle in the TeV range. In fact, actually, many of the papers that TP wrote with Utpal were focusing on this, and they actually studied how one can look for such a heavy dark matter, TeV dark matter particle in future high energy E plus E minus machines. But I, at least in this particular discussion, I'm not going to focus on that option. So let me go before I tell you what option I'm going to look at. Let me also say, how do you look for dark matter at the colliders? The dark matter particles are not going to leave any tracks in your detector. So their production is indicated by an imbalance of momentum. So you produce events with momentum imbalance, and that in the experimental parlance is called missing transverse energy, because at a collider, the PP colliders, PP bar or PP, actually these beams collide, and they come with no initial state. There was no momentum in any other direction other than the beam direction. So therefore, as every child who has studied physics knows, that energy and momentum are conserved, and therefore the final state particle, if you sum over the momenta in the transverse direction of all the visible particles, and you find that they don't add up to 0, then you know that something that your detectors did not capture was indeed produced with a large momentum, and that is how you produce events with momentum imbalance if there is a dark matter that is produced. And indeed, this was actually at the basis of the signature for SUSY particles that had been suggested by DP and Evadria. So there are two types of signals that you can actually give, which are very much dependent on the model, that you can predict and ask the experimentalists at the LHC to look for. You can ask the experimentalists to say, please look for events with missing ET. And so far, we have not found any evidence for that. And therefore, right now, one can forget about it. The other option is direct production of the brothers and sisters of the dark matter particles and their decays. They will not necessarily give rise to events with large missing ET, but they will give rise to some characteristic events. And those, I'll just be back in a second. Ratna, please. I am very sorry that there was a sound and I had to stop it. So the other thing is direct production of the brothers and sisters of the dark matter particles and their decays. And in this case, the specific signatures we look for will depend on the model. And these are the kinds of supersymmetric particles that have not yet been looked for in complete detail at the Large Hadron Collider. So the last one actually depends on looking at rare decays of the Higgs boson. So let me give an idea that the LHC has now produced about 7 million Higgses. Of course, not all of them can be detected, but this tells us that now study at the Large Hadron Collider have turned towards rare decays of the Higgs rather than just detecting the Higgs. So will there be additional exotic decays of the Higgs which decays into dark matter particle? And indeed in supersymmetry, there exist such decays. So question is, can you look for an invisibly decaying Higgs? And this is what I meant by saying that how do you shine a signal where a Higgs is decaying into particles that are invisible to the detector? And indeed, this is something that we discussed and investigated with DP about 20 years ago, almost, maybe 17 years ago. And we had actually suggested, for example, that you could study the associated production of the Z boson in association with the Higgs, where the Z boson decays into its decay products and the Higgs decays invisibly. And then how do you look for such events? And this is indeed that we did. I will show you in half a second. And therefore, right now, the current situation, when the LHC hasn't been unable to see these large ET events that we thought one should see. Now there are only two avenues open for the light dark matter, for the dark matter at supersymmetric dark matter. One is the direct production, as I said, of the brothers and sisters of the dark matter particles. And that is looking for, slightly heavier brothers and sisters of the dark matter particle. And as first, even before that, is looking at the production of a single W and the Z and look for an invisibly decaying Higgs, which can give rise to these final states. And as I said, this is the final state. We did discuss, we did investigate in collaboration with Kajari, DP, and Manoranjan Guchai. And we actually revisited that 10 years after that. So at this point, the Higgs boson was not even discovered, but we said that if there is a Higgs boson, if this is the mass of the Higgs boson, this is how you can look for its invisible decay modes. And indeed, we did it after the Higgs boson was found. We actually did a much more detailed study. Again, with Manoranjan, we revisited the subject. And now, basically, what, let me just come here. And in the frame, what we are really doing now, And that's what I meant by saying that I have focused myself in the recent past on this way for looking for supersymmetric dark matter, one in the decays of the Higgs and the other in the production of the sisters and the brothers of the Higgses at the collider. And about the invisible decays of the Higgs, as I said, we began the investigations with DP. Then we have, more recently, since 2017, we have actually been studying it further and further. So this was the original work that we did with DP. And the idea was that you have one proton and a proton which collide, produces a Higgs and the Z. The Higgs decays into two invisible objects which don't leave anything in the detector. And you just look at the recoiling Z, and from that you try to draw information about the invisible decay products. And of course, as I said, this was done when Higgs was not even found. And this is how particle phenomenology proceeds. Once the Higgs was found, we actually made predictions on the eve of the Higgs discovery that if you can run at the LHC with 14 TeV energy and what is called the high luminosity LHC with a very high luminosity, we said that you would be able to probe if this Higgs had a branching ratio into the invisible channel as small as 18%. Now, what is meant by this branching ratio? The invisible branching ratio means that the probability that the Higgs will decay into these unseen particles. And that is really related, very interestingly, to the total relic density that the model also predicts. Now, that is the implication that I am trying to tell you. I cannot explain this in more detail, but the point is that the same parameters which determine the invisible branching ratio of the Higgs also determine the relic density that that particular point in the parameter space will give rise to. So the combination of these two, what is the limit from the experiment at present and what is the relic density that they're supposed to produce, you can actually look at each point in your model parameter and find out which are the parameters that are still allowed. And that is what we did. And after having done that, we actually decided to then explore what regions. So therefore, what we did is that we took a typical point in the supersymmetric parameter space. We looked at, whether, because there are many parameters and therefore you can actually look at its consequences at the LHC experiments till now. Look at all the experimental information that you have from the LHC on the Higgs decays, also from direct detection. And then you say which region of the parameter space is still allowed. Ask there which of these parameter space regions give rise to the correct relic density. We can also find some region. And now ask the question, how are you going to look for these points in the Large Hadron Collider now? So that is one aspect in which we do. And what we find is that in the PMSSM, there are very small number of points that are actually allowed. However, the story is very different when I go to either non-standard cosmology or when I go to the extended version of the minimal supersymmetric standard model. As I said, most of these details I will discuss tomorrow in my talk. But this is just to show you one very quick picture that these are the number of points in our supersymmetric parameter space that we did investigate. And what we find out of all the points that we investigated, only these few points survived all the current constraints from the LHC, current constraints from the direct detection, and so on and so forth. So this is the kind of type of study that we are doing. And then we actually tried to see how we can explore these points at the high luminosity LHC. And what we saw is that the blue points can still be explored at the high luminosity LHC. However, the orange points are not explorable and they require a proposed extension, which will most likely never happen now, of LHC, which would have been run with 27 GeV. But this is just to give you some idea how one can play with these things. If I don't have complete knowledge of the early cosmology, then of course what happens is what again you want to explore, because all this assumed that the cosmology was standard. And what our investigations were able to show that if the cosmology was not standard, and some of the cosmological assumptions were tweaked, we could still, those points were allowed by observed relic density, we could still explore them at the Large Hadron Collider. So it's almost, showing you the utility of direct exploration of many different types of experiments. So the summary is that for SUSY, a large LSP, that is the lightest supersymmetric particle, is still possible. We can see that the WIMP paradigm for a light LSP is allowed currently by all the data as well as theory. It can be tested at the high luminosity, high energy LHC, at the International Linear Collider, at the Chinese Electron Positron Collider, at FCCEE, and direct detection experiments. And joint exploration on all these fronts can really explore all the regions of the parameter space that are theoretically still allowed. And even the non-standard cosmology scenarios can be tested at the LHC. And this is just one example of the dark matter studies at the LHC. There is an entire big dark matter group, and actually Nishita in TIFR is very heavily involved in it. And this can just tell you how rich the subject of dark matter phenomenology at the Large Hadron Colliders is. Basudev Dasgupta at TIFR works on many, many different ideas other than SUSY, of course. He will always have much more to talk about if you talk to him. But one of the many ideas of my interest is sterile neutrinos as the dark matter. These ideas has implications for structure formation. But the interesting thing for me is that the SUSY partners of the sterile neutrino also offer themselves as good dark matter candidates, and they lead to a light SUSY dark matter particle and hence to a light phenomenology at the LHC. That's also one of the many paths at the LHC in the dark matter phenomenology context to be pursued. So as Sherlock Holmes says, the game is afoot. Experimental explorations for the dark matter and developing a theoretical understanding has the topmost priority in particle physics. It involves particle physics, astrophysics, and cosmology. I have only shown you what the Large Hadron Collider can do, but I'm sure that the experts in TIFR will be able to tell you much more what astrophysics and astronomical experiments can do further. So the quest continues. Thank you very much for your patient hearing.
Thank you, Rohini, for that wonderful talk. Maybe we can unmute ourselves and clap so that we can hear the clapping in the record.
So thank you.
Talk is now open for questions. People who have any questions can either put them in chat or in Q&A, or you can raise your hands. I think Nishita is going to handle the question answer session.
Okay, so while we wait for more hands raised, there seems to be a question on YouTube which asks, could dark matter be a part of Hawking radiation?
I mean, Hawking radiation can be everything, right? It can be a chair. So of course it can be a dark matter. Dark matter can be a part of it.
Yeah.
That's a very quick answer.
Yes, of course. We have more questions. Okay, so while we wait for questions, oh yeah, Gagan has put his hand up. Yes, Gagan, please go ahead.
Yeah, since no one is asking, so I thought I will do the backlight. Okay, so this is a question more related to this your weakly interacting massive particle scenario that you showed that equation. So the question I have, unlike, like the gravitational wave, like you go down on the ladder and you hit the quantum noise and you go further down, and that is what you hit the jackpot. Now, when you do the, you're going down in the cross section. I mean, how? I know there is this neutrino trident or something. I'm forgetting it, but I'm just trying to say that between your WIMP versus the axion-like particle, I mean, can we have some kind of sort of crossover, or somewhere you can say that now it is enough of WIMP and we go something to that, or we cannot do that.
I understand your question, Gagan.
Right.
And that is why I showed those two plots to you of the range of particles and of the range of masses. I mean, there is so much. I can make this generic statement about some two specific classes of models that I might be able to do. I know what you are asking. What you are asking is maybe I can share my screen again and show a plot, which I didn't have. I mean, I purposely avoided it today, though it was, but it was in the slide precisely so that if somebody asks the questions, I can.
Okay. So,
let me share my screen again, and I will show you that plot, and I will comment on the your question. Okay. So what is, and this maybe becomes then clear to others. See, what Gagan is really asking is the following, that for example, what I'm showing here is the direct detection cross section as a function of the neutralino mass. And of course, this is the xenon 1-ton limit. And what is shown here are the predictions of my supersymmetric standard model. Okay. And right now, what you can see for this particular range of parameters, where I have looked at the supersymmetric predictions, then you can see that for almost all the masses above 10 GeV, in fact, the predicted cross sections are above the coherent neutrino scattering. Okay, so this is at least good. Whereas there are some other models, which I don't have a plot here for, unfortunately, because I was reducing the number of technical plots here, which I will discuss tomorrow's talk. I might discuss it, Gagan. So it depends on the particular model parameters space of the model, the parameter space of the model that you're looking at. But in supersymmetry, quite often, all the cross sections that you predict, unless when you are looking at smaller masses, are above the neutrino scattering, neutrino floor. When you go to large masses, which is what I've not covered, and for example, as I said, which is what the folklore is, there the cross sections that supersymmetric dark matter predicts are actually extremely small. And then the kind of questions that you are asking can become relevant. But now from this answer itself, you will realize that the answer depends on the mass of the supersymmetric dark matter particle. So I'm just trying to give you one parameter as an example to show you why one cannot make general statements.
Okay.
The dark matter working group has made certain classifications, and actually you have a in-house expert in Nishita, and she can enlighten you more, and she can throw more light on the subject than me on this model independent analysis.
Okay. Thank you.
Thanks, Rohini. Do we have more questions? So while we wait, maybe I can just say, I was looking at the slides from Morion conference, which is running right now. And in a very interesting signal region, they seem to have positive signal, 3 sigma signal that seems consistent with a chargino of mass 1.1 TeV.
Okay, very good.
There's been lots of caveats, but that seems to be, highlight.
Good to throw some excitement around.
Exactly. Yeah, so
we haven't had some for a long time.
Absolutely.
Okay.
These people are sending around messages.
Yeah.
You remember, Rohini?
Yeah. So maybe, Rohini, I can ask you, do you have like a favorite scenario within SUSY that you think is most likely?
Okay. Now it's a sort of, again, it's a difficult question to answer, but this is more easier than what Gagan asked. Because Gagan's question is almost in principle not answerable because we have this multitude of parameters in SUSY. But I think, see, actually the way I look at particularly low mass dark matter candidates in my own mind is because I wanted to rule out, if you wish, the natural, because what I'm trying to see here is that there is a region of SUSY parameter space, which is natural because the dark matter candidate is small mass. It doesn't matter whether the gluons and quarks are 1 TeV. And it does not require a great juggling of your parameter space to achieve that. especially if you go to NMS system. So therefore, for me, it is important to explore these low mass regions, which we are beginning not to explore at the LHC, saying that, like you said, okay, I try to focus my attention on a 1.1 TeV charge. Of course, I must do that. We all must do that. But the point is, the danger is that we are neglecting the mass of data that exists at the low mass charginose neutral layers.
Absolutely.
And what we have now seen in this entire analysis with Rahul Burman here, and also Ritaja and Biplab and Genevieve Belanger. So we have been doing this and also not just us, there is also a group in Netherlands with Melissa Beckwelt and her collaborators. And I think what we are seeing, to the best of my knowledge, we are the only 2-3 groups which are focusing on this really low mass windows. And you are finding that those regions are still very much allowed. And especially in the direct detection context, it is very interesting from the point of view of the new experiments that are being planned. Because you can actually see signals in that small, because we have many scenarios where you will satisfy all the current LHC constraints, all the current dark matter detection constraints, and you will have phenomenological predictions for the direct detection experiments in the mass region of 1 to 10 GeV. And at the same time, you will have various important contribution signals at the E plus E minus machines. So the point is that there are these regions which we should explore to be able to say that this does not exist. I mean, for me, this is a very natural, quote unquote, natural. I mean, I'm not a great fan of naturalness, but to me, this is a scenario where you have light objects. And then the same thing can give you very credible, interesting phenomenology in the decays of the heavy Higgs. Mm-hmm. And that is also very distinctive. Mm-hmm. Then the LSP is very light. This all I will try to cover tomorrow. So there is a very well-motivated, and that's what you are asking me. In SUSY, is there a well-motivated scenario? And I'm just giving you that there is a well-motivated scenario, which can be tested. And that's the best we as phenomenologists can do today.
That's excellent. We all look forward to your talk tomorrow.
I mean, theory leaves us pretty blind here, frankly, what the masses ought to be.
Okay. So more questions.
Let me just make it a slightly broader one, because of course you focus today on SUSY and tomorrow's talk was also going to be on SUSY. Okay, but of course it's possible, I guess, to have heavy dark matter candidates which are not part of SUSY and which could be seen at LHC. So could we comment on that? Okay. Is there any way of...
That's an excellent question, but on a very generic grounds, I can say 2 things. That the important thing for a heavy dark matter candidate, which is not SUSY, and which is a dark matter candidate, means that it has electroweak interactions only. Because if it had strong interactions, we have ruled out the strongly interacting particles. So therefore, this typical heavy charginose searches can be converted for that. I mean, basically, SUSY to me in this context is only a template. I mean, I like SUSY for other reasons, so I look at it in the context of a specific model. But the signal of a heavy dark matter candidate, which gives the correct relic density, means that it has electroweak couplings. It's right electroweak couplings, right sort of electroweak couplings. Its phenomenology will be no different than a heavy charginose. It will refer in the details, but not in a broad brush heavy dark matter search. I hope I have, I mean, that is why I was going in great details about what is model independent and what is model dependent. And most of the time, SUSY is a template for my other models, simply because I have very specific predictions. That's all.
Yes, if you find one more particle in LHC, it will be very difficult to figure out if it is SUSY particle.
Of course. So we are not, so I don't think that one is going to jump up and down and say one is found supersymmetric. But we will be happy. I will be happy if we find anything at all, right? So the whole point is, in a given framework, if you can look only under the lamp, as it were, street lamp, what is the best way you can define your search strategies? I mean, I think these are two different philosophies as to how one should look at collider studies. And I am just projecting one of the two, I think.
Yeah, I think that's an excellent point of using SUSY as a template, because almost all signatures that you can think of can come from one or another SUSY
scenario.
Point. Yeah. So we have two more questions now. So Govinda first, maybe.
Yeah. So I continue just with your word, Nishida. So actually, my experience in the last 30 years, whenever you see experimental some fluctuations, and there is hundreds of papers explain these fluctuations,
yes.
And after a few days it disappears.
That's right.
How can we prevent it such that people can believe what some theoretician says, that this is the right model, this is the right approach? How
See,
can
Govinda, I think you just have to, I think you have to forgive the vast community of particle physicists who have been baiting with a bated breath, you know. So they all jump. I mean, clearly that, as Amol said exactly, or as Nishita also said, we find something new, we are bound to have 10 different explanations because we have had 50 years to devise theories of different variety, of different principles. And I think it's okay. I mean, actually, I will tell you something, Govinda. I was recently reading for some other reason, the history of discovery, or sort of finalize how V-A was finalized as the theory of weak interactions. And if you look there, and I was reading some of the original papers, and there, of course, facts were just like now. They were also, you know, some 3 sigma signals which had confirmed the tensor coupling of in the decay, in the nuclear beta decay, which was what, I forget. C was one of the 86, which was a gamoteller transition. And it had confirmed it with 3 sigma, okay? And on the other hand, there was people like Sudarshan coming and saying that we know that this experiment gives you a tensor coupling, but we believe that on principles of chirality conservation, it must be V-A. Now, what I should say is that time, a very beautiful guiding principle did show us the way. And that is part of the reason why at least some of the theorists are in the, you know, grips of one principle or the other. Somebody thinks that strongly interacting Higgs sector is still composite Higgs is still a very viable option from the theoretical perspective. Somebody thinks that supersymmetry is a perfect option. And since we have only one piece of datum, you know, it's impossible that we will give you the full-blown theory, right? So I think it's all in the nature of the game.
No. I understand that when you see some signals, we are trying to explain it.
Yeah.
But this looks a little odd that in the last 30 years, any kind of fluctuations, they are always the explanation. So now that when the right signal comes,
I think, Govinda, I would ask this question differently. We experimentalists should provide more signals, Rohini.
Exactly. See, Govinda.
No.
It's okay. I was joking.
I do not agree. Let me finish. I do not agree with that. Whenever you have 100 measurement, there is a chance that 2 or 3 measurement will go above 3 sigma.
Yes.
So that's everybody knows this.
Yes.
So we have been experimentally, there has been many thousands of different measurements. Few of them get fluctuates, and that does not culminate that.
Oh no, what you are saying, Govinda, you are saying something else, which I think I agree with. What you are saying is that our community needs to be more educated. Yes. That's the point you are making.
Yes.
And that I completely agree with you. Okay. But first I was kind of answering it in a slightly lighthearted way that, you know, sort of, if you look at, you know, from 85 onwards, we have been building, designing, and working with experimentalists, working with accelerator people. If we have SUSY, this is what we will see. If we have strongly interacting Higgs sector, this is what we will see. So I think people just tend to go overboard, and you are right that the theory community needs to get itself more educated, and there needs to be more talk between experimentalists and theorists. And in fact, I would like to say that what is happening in B physics is a very good example where there is a very good communication, and frankly also because none of our BSM models fit any of the signals we see. Though consistently we see fluctuations in B physics, none of our models are able to do that. So that is perhaps a better situation than here, where your models were able to, I mean, I can begin from the first day of the Higgs discovery, when the Higgs to gamma gamma was more than what standard model had predicted. And that was like, the sort of a red cloth to bull for all of us, right? So, that's the way things are going to go. But I agree with you.
Thank you.
That the phenomenologists need to learn a bit from the experimentalist colleagues. If that's what you're saying, I'm in complete agreement with you.
Thank you.
Thanks. So Basu has his hand up. Basu, would you ask a question?
Yeah, I'm scared for any question that you will ask.
So I have a maybe half technical question. So are there types of dark matter that something like LHC, a collider, is well suited to look for, but that doesn't fall in the category of, say, self-conjugate, Majorana type dark matter? So like I'm thinking of something like asymmetric dark matter. Like,
Yeah.
you have some comments about that? Like what?
Okay, I mean, I have not studied it in great detail. I have only looked at papers and flipped through things. But yes, actually for specific scenarios, there are actually well-defined signals. So see, because one thing about LHC,
in the sense that it's heavy, it has weak interactions, but it doesn't self-annihilate. So I don't have to worry about the relic density constraint, which rules a lot of,
that actually releases you from any bonds. And that my answer is same as what I gave to Amol. That a typical weakly interacting particle search.
Yeah.
I mean, it is certainly not strongly interacting. That we know for sure. I mean, that our, Kajari and her friends have told us that 100 times now. So we cannot think of a strongly interacting lightish dark matter.
But maybe I slightly add a bit to my question, that are there parts of the SUSY space which give you such a candidate?
As I said, as far as the LHC searches are concerned.
No, from the SUSY theory side.
Oh, actually, if I, okay, I understand your question now. If I remove the relic density constraint, that's one of the angles which I didn't pursue too much, but I have in mind to pursue. For light dark matter, we looked at in the PMSSM. And then the LHC collider scenario changes substantially when I remove the relic constraint, because the couplings of this guy to the W's and the Z's are different than what a guy which gives me the right relic or not too much relic would have. So the signals that I get, in fact, the plethora of signals is much more, and they produce many more leptons more happily. And in fact, it can be seen more easily and hence ruled out more easily. So the current constraints rule a major parameter space there rather strongly. And what is to me interesting enough is that at the HLLHC, for this limited region that I had looked at, I have signals, and HLLHC will be able to probe it. Now, the kind of question you are asking in this language is an interesting question, but it hasn't been asked in this particular form.
Rohini, can I make a comment?
Yes.
If someone releases yourself from the paradigm of minimal particle content, it's trivial to build such models. Building models is never a challenge. It's just, but the question is that, well, why are you doing this?
Why am I keeping myself to minimal particle content?
No. The question is that why am I want to include, extra mechanism, extra things, and I mean that's what you self-restraint comes in terms of working with minimal content, minimal symmetry, minimum extension. But
yes.
Yeah, if you release yourself from it, building models which suits you is trivial.
No, but then the point to him is, one just does not want to build models for the sake of models, right? I mean, one wants to at least begin from a principle. At least that's what from a theory side. I think that is the kind of question that Basudev was also asking. I'm sure you also have the same thing in your mind. I don't have to sort of expand on that for you. point is that you begin with a principle and you ask a question, because we have this somewhat ugly, but at the same time, very beautiful structure of the standard model. Okay. And at least what I have learned, and again, I would go that this is because of my recent interest in how V minus A developed. I studied quite a bit. What I have learned is that I would respect experiments. And that is why I agreed with Gagan that I would love the experiments to give us more to work with, whether they are LHC experiments, whether they are experiments in the space, from various space-based experiments or direct detection. And that is where, to me right now, if you ask me, I would put more money in building a detector which detects a dark matter particle between 0 and 10, even if my theories say that that should not exist. This is what my gut tells me. So therefore, I don't think that it's a big surprise if I add a few more parameters to my model, very well motivated parameters, that I will be able to satisfy all the non-observations. But that's not the game. The game is, what can you see? And what can you do to test what you are putting in? At least that's my approach as a phenomenologist.
Thanks. I guess we're closing up on the time. So Shrirup has the last question for the session.
Okay. So this is something which has bothered me, Rohini. We look for dark matter at colliders by looking for a missing energy signal. Now, when suppose I do see a missing energy signal, how do I know that it's a genuine dark matter candidate and not just a long-lived neutral particle? And what test could we do for this?
No, that's a good question. And actually, you have touched upon, and you know very well, touched upon the second important part of phenomenological studies at the Large Hadron Collider, and that is the study of long-lived particles.
Yeah, but I'm talking about long-lived neutral particles.
Yeah, long-lived neutral particles also. In fact, the thing that I mentioned, for example, when a heavy Higgs decays into neutralinos and charginos, and then some of them become long-lived, there are actually neutralinos which could be long-lived.
Yes. But so I would just jump up, as a typical theorist of the kind which Govinda doesn't like, I would jump up and say, this is a dark matter signal. But of course, this question would arise that is it the same as the Rayleigh density, or is this something?
With one detection, Amol made the important statement. With one detection, we are all hoping that we'll get at least one. We cannot build. It's like saying that in a Lego puzzle, you have only one stick.
No, I understand.
And you can close it any which way you like. You can put it on the ground horizontally, or you can put it vertically and say something needs to support it.
Say that, okay, I need this shape of piece to fill it in. So do we know what that shape is? I'm just asking, you've done a lot of work with this heavy Higgses and...
there are pieces and bits and pieces. For example, you yourself, you are giving the answer, you know the answer. That if you do heavy Higgs phenomenology, that is, you look simultaneously for long-lived, since you are asking. My generic answer is the following, at LHC. One must look for a dark matter-like signal, whether it comes from a disappearing, large ET, the classic missing. Then you can have the neutral signals which stop particles decay in the, traversing some distance. So that is this whole story of LLPs, guys which decay far away. So you look at things like, what are those, phaser and those experiments. So Mathusla.
If you're lucky.
You have to do all this phenomenology and you look for it. You look for it, okay?
Absolutely, if you're lucky.
If we are lucky. Because I think whatever we thought on well-behaved models, we have not found it. That is, let's face it, but that doesn't mean that it is not there. That is the problem. And we are going to have this machine for next 20 years.
Anyway, I guess you'll tell us more about that tomorrow.
I hope so, but I have already talked quite a lot about what I will say tomorrow.
Okay, thank you everybody for the very interesting discussion session. So I hand back to Amol the mic.
Thanks everybody for coming here. Let me formally thank Professor Godbole for this wonderful public lecture. Of course, we'll hear from you tomorrow again in our colloquium. However, of course, it would have been great if you were present in person. You know that you are always welcome whenever time suits you. Okay. I also thank Mrs. Roy and the family of Professor D.P. Roy for starting this lecture series and for the TIFR endowment for implementing it. Thanks are also due to my fellow members of D.P. Roy Memorial Lectures Committee, Professor Shaurendu Gupta, Manoranjan Guchait, and Tuhin Roy, who did not appear on the screen but have done a lot of work behind the screens. Of course, to Nishita for handling this session, and Ajay and Kapil especially for arranging with the Zoom. So thank you everybody. Thanks all for being here, and see you hopefully very soon.
So guys, great, and thank you. It was nice seeing you all and talking with you all. Maybe one of these days we shall actually meet each other. Inshallah.
Yeah.